We've been learning lots of different rules to take derivatives, so we don't have to use that formal definition of the derivative anymore. And the rules that you see on the screen are the ones that we've covered so far in class. Today, we're going to look at a new rule called the chain rule, which is going to make our life a lot easier, and it will help us be able to take derivatives of functions that we wouldn't been able to take the derivative of without this chain rule. Before we get into the chain rule, I kind of wanted to go through composition of two functions, because the chain rule uses the fact that the function that we're dealing with could be rewritten as a composition of functions. And so we need to be able to recognize what functions can make up, if we compose it, take the composition of the two, the original function we're given. So let's just go through and just recall really quickly from algebra what that means, a composition of two functions. And so if you have two functions, f of x and g of x, the composition of those two functions can be written in a couple of different ways. So the composition of the two functions can be written as follows. So you might see this F and then a little circle in between that F and the G, and there's a parentheses around that F, little circle G, parentheses, and then an X in parentheses. What this is meaning when it's written this way is you have your function f, and inside you're going to go in and you're going to plug in g of x wherever you see an x in f of x. So we can write that as f parentheses g parentheses x and both of those parentheses. So really, when we were looking at maybe back a part of the difference quotient, right? Let's say f of x was equal to the square root of x minus 2 here. And let's say g of x was equal to x plus h. And we wanted to find f of, I kind of like this way of writing things a little better than this way of composition, just because it makes it easier, kind of what you're doing. You're plugging in the function g of x. So if we find f of g of x, and it reads off f of g of x, then this is saying we're looking at f, and we're going in wherever we see an x in f of x, we're plugging in what g of x is. X plus h. So if we go in here, we have f of x plus h is equal to the square root. Wherever we see an x, we're going to put parentheses, and we're going to replace that in a second with x plus h. And then minus 2. So x plus h. So the composition, we've pretty much been doing composition of functions as part of that difference quotient. So let's give another example, and then let's go backwards. So let's say we have f of x is given to us as x squared minus 2x plus 1. And g of x is defined as the function, let's just do the square root of x. And it asked you to find f little circle g of x. So we can rewrite this. This is f of g of x which if we telling me this is the same thing if I want to rewrite it as, well, my g of x function is the square root of x. So I'm going to go into my f of x function, and wherever I see an x there, I'm going to replace it with the square root of x. So doing so, I see an x, put parentheses squared, minus 2. I see an x, so parentheses plus 1. Go in and plug in square root of x. And we can simplify that a little bit. We have the square root of x quantity squared is x minus 2 square roots of x, and then plus 1. So we just found the composition of f of g of x. I want you to be careful though, because order matters for composition of functions. If we had rewritten this and it had asked us to find this g of f of x, in this case, we would be rewriting this. This is the same thing as g of f of x. So our g function, we have g of the f of x function. And our f of x function, if we look up here, is x squared minus 2x plus 1. So we're going into our g of x function now. And wherever we see an x, we're going to replace it with f of x. So doing so, we have the square root. I see an x there. That's the only thing that's underneath the radical. So I'm going to replace that x with what f of x is, x squared minus 2x plus 1. I actually noticed that simplifies. This would not give me the exact same thing above. Be careful when you have a sum or a difference of terms underneath the radical, you can't just take the square root of each piece and add and subtract. So just be very careful. This does not equal the square root of x squared minus the square root of 2x plus the square root of 1. But if you notice that trinomial underneath that radical, there are two numbers that multiply to positive 1 and add to negative 2, which are negative 1 and negative 1. And so this is the same thing as x minus 1 quantity squared. And because everything is squared under there, that parentheses, we can cancel out that square root in the square, and this is equal to x minus 1. So notice the opposite direction, g of f of x, was something totally different than we got for f of g of x. So order matters there. Okay, so that was a quick review of composition of functions. And that's what generally the way that we went in an algebra class. We were plugging in a function into another function. What's going to be helpful for us, though, is to go backwards. So given a function, can we manipulate it? And sometimes we don't want to, but can we manipulate it to be a composition of other functions? So let's look at an example of that. So let's say we're given a function h of x. This is equal to the square root of 6x minus 1. And it asks us to find two functions, f of x and g of x, such that if we took the composition of the two, and order matters, so we have to decide which way we want to write it. So let's say f of g of x. That would give us back our original function h of x. So right now, if we look at h of x, we do not know how to, and we cannot take the derivative of that function yet. If it was just the square root of x, we could, but right now we don't know how to take the square root of anything other than just x underneath that radical. So let's, actually, that's not necessarily true. Anything that is more than one term under that radical. So let's go in here. And what I just said, we couldn't even do that all the time. Anyways, that was just kind of catching me that I was like, that's not totally true what I just said. G of x, this inner function. So if you have a radical, choose that inner function to be everything underneath that radical. If you have parentheses raised to some power and there's some function inside that parentheses, make that be what's inside the parentheses, your inner function. So we're going to choose in this case, g of x to equal 6x minus 1. Well, if that's the case, then notice that h of x right now is equal to the square root of g of x. So we want to be able to find our outer function f of x. And to look at that, it's going to be wherever we see g of x in here, we're going to replace that with x. So we're going to choose f of x then to be the square root of x. And so we can test it. And show that it works. Our h of x is equal to the square root or f of g of x. So this is the same thing as f of g of x, but if I look at my g of x function, g of x was 6x minus 1. So let's rewrite g of x as 6x minus 1 in there instead. Now, if we go in and we see an x in our f of x function, we're going to put parentheses. So this is equal to the square root. I see an x there, so put parentheses because we're going to replace that with g of x, which is just 6x minus 1. Which notice is the same thing h of x is. So we chose the right things to be, we chose two functions that if we took the composition, we would get back the original function. There are multiple ways to choose. So we could choose different functions and it would work, but we want to choose things that are going to help us when we're going to take the derivative. So always choose the inner piece to be like what's underneath the radical, that whole thing, or for instance, if we had h of x was equal to, just in case you need to write down that, parentheses 4x squared minus 9 raised to the 10th power. So this is actually something we could manipulate and take the derivative of. We don't know how to take the derivative right now of this without having to expand this and take the parentheses and multiply that out 10 times, which if that power is big, that's going to be kind of tedious. And we don't really want to deal with that. So if we can rewrite this as a composition of two functions, then we can use the chain rule, which I haven't defined yet how to do that. So in a minute we will. So again, we want to find f of x and g of x such that, so a lot of times in mathematics, such that you'll see as just the s dot t dot, such that our composition of the two functions equals our original function. So h of x is equal to the composition of f of g of x. So I tend to go with the inner first. inner is going to be what's inside the parentheses. So we're going to choose our inner function g of x to equal this 4x squared minus 9, which means my outer function, f of x, is going to equal, well, wherever I see the inner function, I'm just going to write x there. So I'm going to want to put in this whole function wherever I see an x. So I'm going to put x here. And so now when we take the composition of the two, f of g of x this is g of x raised to the 10th, or this is 4x squared minus 9, all raised to the 10th, which is our original function, h of x. So these are the two functions we needed to find. This other work right here is not necessary. I'm just showing you that we did choose the correct functions, that when we took the composition, we got back the original function.